This is rate equations 2 in 3 minutes.
The rate equation is an equation that relates reaction rate to reactant concentration and is different for every reaction. So for example, if you had a reaction A plus B goes to C plus D, in your rate equation you would have concentrations of just the reactants A and B. Before that you would have the rate constant K, and each reactant A and B would be to the power of a number, M and N in this case. These are the orders of A and B. The rate constant K in rate equations have variable units, meaning the units changed based on what the reaction is. So let's say we have the following equation and we're given this table of results for the initial rate method, and we find the reaction is second order with respect to NO, zero order with respect to CO, and zero order with respect to O2. To find out the value of the rate constant K, your first step would be to write the rate equation.
So that would be K, NO squared because it's second order, CO to the 0 because it's 0 order, and O2 to the 0 because it's 0 order. And because anything to the power of 0 is equal to 1, you can cancel out CO and O2. This gives us rate is equal to K, NO squared.
Your next step to finding out K is to rearrange the equation to make K the subject, so that gives us rate over NO squared. And the third step is to sub in values from your table into your rearranged equations. You can pick any experiment from your table. So for example, if we use experiment 1, our values would be K is equal to 0.176 divided by 2 times 10 to the minus 2 all squared. And this gives 440. As the units of K are different for every reaction, our fourth step would be to find the units of K. To do this, we use the rearranged equation and we sub in the units for rate and concentration. So at the top, the units for rate is moles per dm cubed, seconds to the minus 1. We can group the moles per dm cubed together to make it easier to cancel out. And at the bottom, we have a concentration squared, so that would be moles per dm cubed squared. We can now cancel out one set of moles per dm cubed from the top and one from the bottom to give us seconds to the minus 1 times 1 over moles per dm cubed, which is dm cubed over moles. And as anything at the bottom of a fraction is to the power of minus 1, we can say that moles is to the power of minus 1, and dm cubed and s is to the minus 1. So the full answer is 440, moles to the minus 1, dm cubed, s to the minus 1. So the size of the value of the rate constant K tells you how fast the reaction is occurring. So the higher the value K, the faster the rate of the reaction. So if you increase the temperature of a reaction, it means the reaction will happen faster and K would be larger. Now the rate equation of a reaction can give information on how the reaction mechanism looks like. A mechanism just shows the different steps within a reaction. So for example, if we had A plus B going to E plus F as an overall reaction, the reaction could be split up into two steps. Step 1 being A plus B goes to C plus D, and then product C plus D in step 2 react together to form E plus F. Now every reaction has a different rate, so we can assume that one's faster than the other. So if step 1 is faster than step 2, we can say that the first step happens so fast that it does not affect the rate. This means that in the second step, we can assume that the reaction is happening so slow that most of the time in the reaction is spent in the second step. So we always call the slowest step the rate determining step, and this is what affects the rate of the reaction. This means that in your rate equation, you should only have the reactants of the rate determining step present. So in the above example, step 2 is the slow rate determining step, so the reactants C and D should be present in the rate equation. A and B are not present as they are in the fast step, and they don't affect the rate. To find M and N, which are the orders of C and D, you can use the balancing numbers in front of C and D in the rate determining step, which in this case is 1 as there's no numbers, so both would be to the power of 1. So let's say we have the following two-step mechanism and we wanted to work out which step was the rate determining step. Let's say we're also given the rate equation as rate is equal to K times Cl radical times O3. We can tell that the slow rate determining step must have 1 mole of Cl radicals and 1 mole of O3 as they're both to the power of 1. This would mean that the slow rate determining step is step 1 and the faster step is step 2, as ClO radical and O radical are not present in the rate equation. This was obviously a very quick summary. For a longer, more detailed explanation of the topic, check out the link to the full lesson and subscribe to my channel.